Over and over again, my physics students will say to me, I just don't get the photoelectric effect. And why is this? Well, I think there are several foundational pieces of information that you have to have clearly in place if you've got a hope in heck of understanding this topic. Please let me know in the comments below if you think this attempt of mine to simplify things has helped you. But don't forget, some of the greatest minds in physics, when this piece of work was first done, spent some time sitting around scratching their heads together trying to work out what was going on. So if it confused them, give yourself a break. It's going to confuse us too. The really big deal with this photoelectric effect is that it is evidence that light behaves as if it's a particle. Remember that old argument that still rumbles on just what actually is light. The first of my basic points that you have to understand in order to grasp the photoelectric effect is all about the electromagnetic spectrum. You need to be fully aware that the electromagnetic spectrum is considered to be made up of tiny, discrete little packets of energy called photons. The order of the spectrum is dependent on the frequency of these photons. And we know that the energy of these photons is given by E equals hf, where h is Planck's constant. If you are ever unfortunate enough to be hit on the head by a tennis ball, you will know that you feel a short, sharp shock. This is because the tennis ball is a particle, and particles, when they collide or interact, can give up some of the energy. Clearly, the tennis ball comes zooming in, hits your head, gives you some of its kinetic energy, and bounces off with the remaining energy. Photon interactions are completely not like this at all. They are what we call a one-to-one affair. So if a photon comes flying in, it hits the particle, gives up all of its energy, and ceases to exist. Now that we've seen that the photon interaction is one-to-one, all or nothing, let's consider what happens if you turn up the intensity of a light source. Firstly, consider a sound wave being produced by a loudspeaker. You know the cone goes in and out, produces rare fractions of air. We draw this as a sine wave for convenience. So, as we turn up the volume of the sound, the amplitude of the waves increases. More energy, louder sound. But you can't take this logic and apply it to a photon, because if you turn up the energy of a photon, its frequency will change. And so, if you want to make your light brighter, you would imagine that the colour would change, but it doesn't. What happens if you turn up the intensity of a light source is that you create more discrete little packets or photons with the same energy that you had originally. So in other words, turning up a light source, making it brighter, does not increase the amplitude of the photons. No, it doesn't. What it does do is just increase the number of them. Point number 2 in my fantastic list of things to understand about the photoelectric effect is the structure of metals. That worn out and overdone topic that you think you know all about. We know that in a metal like copper, we have a whole pile of copper atoms in a nice neat lattice, though really we should call them copper ions, because each of these atoms or ions donates 1 or maybe 2 or a small number of electrons to the sea of delocalized electrons around it. Now, this word delocalized means not local. In other words, free to travel away from the local area. And so these electrons, they zip around all through the structure, having collisions here and there with some of the other atoms, or indeed ions, and even with each other probably. But do remember that my diagram is absolutely nothing like it really is. Apart from anything, it's completely not to scale. We're talking models here, like we do all the time in physics. And this leads me to another important point that's often confused here. Naturally enough, these copper ions have a whole pile of bound electrons that orbit, in speech marks, the copper ions. And these bound electrons play virtually no, if indeed no, role at all within the photoelectric effect. So don't get confused between the delocalized electrons and the bound electrons. Point number 3 in my essential list to understand is to consider how waves deliver energy. Energy is delivered continuously by waves. Now, you know this is true. If you get a chess ball and put it outside in the sunshine, if we ever get any, then you will know that the black squares on that chessboard are going to warm up gradually. In fact, they can get quite hot. And this is because they are absorbing the infrared waves that keep falling on them continuously, over and over. Pluck a guitar string and you'll see the string vibrate like this. And as it's vibrating, you hear this continuous tone. Consider too that loud sounds waves can cause things like wine glasses to build up such a big vibration that they just shatter. And now we have arrived at the place where we can begin to talk at last about the photoelectric effect itself.